Here's a fluid mechanics question which explores the idea of hydrostatic pressure while the liquid is not actually stationary. And in addition to that, it adds this spring into the mix as well. And then we're going to look at what happens when we have a certain spring extension at the beginning, which is given to us by an amount x0, and then we're going to look at what happens to this extension when the whole tank, including the object and including the water inside, will start accelerating upwards with a certain acceleration a. Okay, now this is the kind of fluid mechanics question which you might get if you're a first-year student doing something like undergraduate engineering, whether it's aerospace or mechanical or ship science, or it might be the kind of question that you might get in high school if you're preparing for something like an Olympiad or a competition. And if you'd like to see anything similar to this on the channel, let me know in the comments. So here's how we tackle this problem. We're dealing with a cylinder which has a cross-sectional area of S, and that cylinder is connected to the bottom of the vessel via a spring, which has a stiffness K, 10 newtons per meter. And when some water is filled in the vessel, the cylinder floats partially submerged, and we know the extension is x0. So the question doesn't really tell us anything about values. Okay, we have the spring constant is 10 newtons per meter, but that's about it. So the first thing I would do here is I would write down, or I would draw the free body diagram before that whole vessel is being accelerated. So I would draw the cylinder like this, and I would draw what are all the forces that are currently acting on the cylinder. So let's say that right now the water level is maybe here. Okay, we don't know how much of the cylinder is submerged, so we're just assuming a couple of things. So we know this has a weight, which is mg. So that's one force acting on it, but there are two more things. So the other one is the upthrust. So the upthrust is acting, of course, upwards, and that's the buoyant force. So I'll call this Fb. So that's the weight of the displaced liquid, which is rho of the water times g times Vd. So that's the volume of displaced liquid. And that is, yeah, so that's how much we know about the problem so far. Okay, and there's also the spring. But what I want to do right now is I want to rewrite this in a slightly different way. So instead of writing Vd, I'm going to use the fact that this object is a cylinder. So because it's a cylinder, we can find the volume using the equation of the volume of a cylinder, which is height times the cross-sectional area, right? So I wanted to convert this volume into something using this S that we assume that we know, that the problem tells us that is a known variable. And the H is, of course, how much of the cylinder is submerged at this given moment. And then what happens is this spring is extended, which means if it's extended, then the elastic force is going to act downwards towards the bottom of the tank, and the value is going to be kx0. So what we can do now is we can write Newton's second law, taking into account that this has right now zero acceleration. So the object has zero acceleration, meaning that the forces are canceling each other out. So we have the upthrust minus the weight, and then minus kx0 equals 0. So that's the first thing that we're going to use. And the other thing is what happens when the tank starts accelerating upward. So what I'll do is I'll draw two things. So first of all, this is going to be the cylinder at the beginning, that is before the tank starts accelerating. So I'm going to redraw it like that. And In the second scenario, when the water tank is accelerating upwards, we're going to assume that the cylinder is submerged more. Now, although this is an assumption, it doesn't really take away from the generality of the problem, because what we're actually interested in is what happens, or by what amount will the length of the submerged portion change. So if we assume that the cylinder will submerge more, it means that that change in depth will be positive. So if we assume this is more and the final result is actually positive, it means that indeed the cylinder will be submerged more. If the final answer is negative, it means the cylinder will get out of the water instead. So let's just carry this assumption forward in the case when we have a vertical acceleration. So in this case, the new depth is going to be h plus, let's call this delta h. And it's this delta h that the question is asking us to find an expression for when the water tank and the cylinder and the water and everything is now accelerating upwards. So those are two scenarios. In the first case, we had an acceleration of 0, and now we have an acceleration upwards, which is non-zero. So what I would do here is essentially just draw another free body diagram on the slightly more, perhaps, submerged cylinder. So first of all, we have weight, which is acting downwards as usual. And then we have the elastic force. Now the elastic force, I'm going to say it's still downwards. The initial extension of the spring was x0. So if the spring was extended by an amount x0 this way, and then the tip of the spring is moved downwards by an amount delta h, then the spring is still extended, by it's extended less. So it's extended by x0 minus delta h. That's going to be the new spring force. And the other thing is the upthrust, or the buoyant force. And here's where we have to be a bit careful, because the new buoyant force, you just move this out of the way and just put it here. The new buoyant force is also based on the weight of the displaced fluid, but now the displaced fluid, or the fluid in general, weighs more because of the acceleration. So we still have density, but now we don't just have g for acceleration, because there's an added vertical acceleration on top of that. So the perceived gravity is going to be g plus a. And then, of course, the displaced volume is going to be h plus delta h multiplied by s. And that's it. So we can write Newton's second law for this, which is essentially rho w. So all the forces acting along the vertical direction, the first one being this, and then the other two being acting downward. So that's minus mg minus k, and then x0 minus delta h. That is equal to the mass of the cylinder times the acceleration. And that's it. So that's literally F equals ma, where this is F, or the net force, and that's the mass, and that's the acceleration. So we're going to use this as well as this first initial equation to figure out what that delta H is, what the expression for delta H is. So let's actually take this and let's maybe expand some brackets. Let me first of all take this to the next page. Right, okay. So I'm going to expand some brackets like this. So I'm going to say this is rho w gh, and then I have plus rho w, let's not forget about the s here, rho w g delta h, and then we have plus rho w ah plus rho w a delta h, and the whole thing is multiplied by s. And then we have minus mg, and then it's minus kx naught plus k delta h and that's equal to MA. Now, this is not particularly hard. There's just quite a few terms to keep track of. And to simplify this slightly, we're going to use this first equation, which says that when there's no acceleration, rho WGHS minus mg minus kx naught are equal to 0. So we can use this straight away and cancel out some terms in the equation above. So we can cancel out this minus mg as well as minus kx naught. And whatever we are left with, that's how we're going to try and find delta H. So in the remaining expression, we have this term containing delta H, as well as this one and this one. So let's factorize the delta H, and let's see what we're left with. So delta H is rho WG, and then plus rho WA plus K. And on the other side, I have just MA minus rho WAH. Right. So let's take this and let's play around with this a bit more. So delta H, therefore, is A multiplied by M minus rho WH divided by... So what we can do here is we can factorize rho W. So this is going to be rho W G plus A plus K. Normally this would be the final answer, but it doesn't really work this time, because if you read the question carefully, we're not being told anything about the mass. So we don't know how much the mass is. It's not even specified as m. So instead what we have to do is we have to use other variables and substitute for this m here. And we can actually do that. So I'm going to take this first equation again where m appears, and I'm going to find m. So that equation is, let's draw a line here. So we have rho WGHS minus mg minus kx naught is equal to 0. So mg is going to be rho WGHS minus kx 0. Therefore, m is rho WG, there's no g, there's hs minus k over gx naught. Okay, so that's it. That's the mass that's the expression for mass that contains everything else that we need. So we take this and we're gonna put this where the m is, right? Because we don't know anything about m, so we're gonna do the substitution. And this is what we end up with. We end up with delta H equals A times, and then we have m, which is now equal to this thing. So rho WHS minus, and that should have been k over gx naught. So k over gx naught, and then it's minus rho WHS, and this is divided by k, or let's write this first, g plus a and then plus k. So you should notice that this and this cancel out, and we're going to end up with the following. So delta H is going to be minus, we can put the minus in front, and then we have k a x naught over, and then this g I'll just put in the denominator, and it's g multiplied by k plus rho w g plus a. And that's it. So this is the change in depth, or the change in how much the cylinder has submerged based on things that we know. So everything in this equation has been provided to us in the question. And as you may notice, the final answer is negative, which means that the only way in which this change in depth is negative is if our initial assumption was not correct. So what this means is the depth decreases. So when the tank is accelerating upwards, actually the situation looks a bit different than what we drew earlier, and namely it looks like this. So the cylinder is now leaving the water more than in the first case when there was no acceleration. So it doesn't submerge more, instead it rises above the water level. And that's what the minus sign here says, but everything else is the same. So the actual amount, the magnitude of that change in depth is equal to this, which is based on variables, parameters that the question provides us with. And that's the end of the question.